Hi, well, I'm Stephen Neshiba, and I'm here to help you out with predicting moments of Vx using the Boltzmann probability density that's given by Fb of Vx. And the general formula for moments are using these brackets. That means the average. So Vx raised to some power, 1, 2, 3, gets put into there in the integral, and then the average is given by that evaluated integral. Now all we're up to today is to decide whether or not those moments are 0 or not 0. So to make that happen, just by inspection, what we would need to do is graph out the integrand, and that's the integrand. And so that's what we're going to do first. Now the Boltzmann function, that's just a Gaussian bell-shaped curve, and that's fine. And I've drawn that there, and now to get the first moment, that would be Fb times V to the first power, and so there's V to the first power. And if you want to give a shot at what the integrand looks like, take a pause right now and graph out what the product of Vx times f of b is. Okay, well, if you've done that, then here's how I go about it. I just go over this entire range of Vx and say, okay, well, if I multiplied by Vx times anything right here where Vx is 0, then the product is obviously 0. And let's see, as I go up to the right, I have a positive number, Vx, times a positive number, Boltzmann function. So positive number times a positive number is a positive number. So I know that I'm going to sort of be moving up over there. And then how does it, what's the asymptotic behavior? Well, I have a declining exponential function, Gaussian function, times a linearly increasing polynomial, in this case just v, and exponentials always kill polynomials. Therefore, that result has to go off to 0 on the right. And now what's it going to look like on the left? Well, I have just the same thing, but instead of a positive number, I've got negative products over there. So I'm going to draw it like this. Okay, and since the integral is the the area under that curve, just by inspection you can see that that mean of v has to be equal to 0. Okay, how about this one? I'm looking for the integral, or the second moment, the integral of Vx squared times the Boltzmann function. So if you want to give it a little pause here, first thing to do would be to graph what Vx squared looks like. Okay, that's pretty straightforward. That's just a parabola, which I'm going to draw there. Okay, so that's Vx squared. Now, what does the product of Vx squared times the Boltzmann function look like, if you want to give that one a shot? Okay, I'm going to use the same method that we did before here. I'm just going to go over all the range of Vx and say, oh, look at this. When Vx is 0, then Vx squared is 0, and that times anything is 0. So I get to plant a certain point right there at 0. How about the asymptotic behavior to the right? Same deal. I've got an increasing polynomial times a declining exponential function. So, and it's positive times positive, so I must be looking at something that goes like this. Okay, and then what does it look like as we go to the left? Well, it's actually perfectly symmetrical. So I've got something like that, all right? And the area underneath is equal to Vx squared, and obviously it's not 0. If we wanted to actually evaluate it, then we'd look at an integral table, something like that. How about this last one right here? I'm interested. It's not a moment. It's some other average. I'm just interested in the average of sine of some constant times Vx, a sinusoidal function. So if you want to give this pause and try this one out yourself, what you would do is sketch out the sine function, take the product, and look to see whether it's the result is symmetrical like this or anti-symmetrical, in which case you get 0. Okay, here's how I'll do it. First I'm going to graph out the sine function. I know that a sine function looks like this. Okay, that's depending on the wavelength, which will be governed by A. Okay, so that's the sine function. Now, the sine function times that Gaussian function, same kind of deal. I got 0 times something at 0. I've got positive numbers here that go back to 0 here, and I've got an asymptote of 0 off to the right. So, and here I've got positive times a negative number. So I think that my integral will look something like that. Okay, and so on. And then off to the left, what is it going to look like? Well, same deal. I'm going to have negative and so forth. So I hope you can see that whatever positive area this contributes, that'll be canceled out by a negative area, and that'll be true for the rest of the curve. Therefore, the mean of sine of AX is also equal to 0. And that's how you do all that sort of problem.